In the previous video, we talked about the P-N junction. In the P material, the predominant charge carriers are holes, which I'll represent by the symbol X. In the N region, we said we had a predominance of electrons as charge carriers, and I'll represent that by this dashed line. Now we said that some of the holes would diffuse to the right and the electrons would diffuse to the left. And when that happened, we set up an E field at the junction. And this E field opposes further diffusion of carriers. So we said that we developed in the junction a depletion region that was depleted of carriers. Now I want to ask, what happens if we have a difference in concentration between these N and P regions? Let's say, for example, we have a high concentration of dopant for the N region. So we have a large surplus of electrons. But in the P region, we have a very low concentration of impurities. Well, what's going to happen is these electrons have to migrate further into the P material to recombine with the hole. So that these electrons will maybe have to wander way over here to recombine. So what happens is, because this region, the P region, is lightly doped, that the depletion region extends further into the region that is lightly doped, where the concentration is smaller. And at the junction, the depletion region is smaller into the N region, where the concentration of carriers is higher. So let me erase this. Let's redraw this P-N junction region. So on this side I have a P material. On this side I have an N material. And at the interface between the P and N region, I have a region called the depletion region that is devoid of carriers. So this is the depletion region. You can think of this depletion region as being an insulator. So if that's the case, the P region is a conductor and the N region is a conductor, and I have a region between these conductors that is an insulator. So remember the capacitor. So here I actually have a capacitor. I have a P terminal, I have an N terminal. This region can be thought of as a plate on a capacitor. This N region can be thought of as a plate. So I have a plate and a plate. So this P-N junction has the characteristics of a capacitor. Now recall that the equation for capacitance is the Greek letter epsilon times the area of the plate divided by the distance between the plates. Now the distance between the plates is this distance here, d. And this distance between the plates is the dimension of our depletion region. But besides being a capacitor, this P-N junction region also forms a diode. And the symbol for a diode is this. And this region, the N region, is sometimes referred to as a cathode. And the P region is referred to as an anode. And the diode allows current, positive current, or what we can call whole current, to flow in the direction of the arrow in the diode. So this is the direction that positive current will flow in the diode. And the diode will block current flow in the other direction. So let me erase this. Now let's analyze what happens in this PN junction when I apply an external voltage. So here I have a battery. I'm going to connect the positive terminal to the P region, and the negative terminal to the N region, and I'm going to plot the current in this diode versus the battery voltage, V. This is the direction of the current. Now, if I start at 0 volts for the battery voltage, I'll be operating at a point here on the current versus voltage curve. Now, as I increase this voltage, recall that we have a built-in E field in this depletion region. And as I increase the battery voltage, I'm making this P region more positive relative to the N region. So in effect, I'm canceling out this E field that's built into the depletion region. And as I increase this voltage, I move out here, I increase the voltage a little more, I move out here, and eventually I collapse the depletion region, and at that point I get current to flow from the P region to the N region. So I get a current flow, and if I increase the battery voltage a little more, the current continues to increase. So I get a curve that looks something like this. And this voltage, where it starts conducting, depending on the diode characteristics, it could be around 0.5 volts. This may be 0.6 volts. Out here, perhaps this is 0.7 volts. So let's analyze what happens if I reverse the polarity of this battery. So I'm going to remove this battery. I'm going to connect one with the opposite polarity. So let's connect this terminal to the P region. I'm going to connect the positive terminal to the N region. So this has been deleted here. So what's going to happen now? In this case, I'm creating a positive region in the N by applying this external voltage, and a negative region at the negative terminal of the battery. So in effect, I am reinforcing this electric field that was built into the junction, and I'm making this depletion region wider. And when I do that, if I plot the voltage that's reversed in this direction, I get extremely tiny current flows, almost unmeasurable. If I keep increasing this voltage in this reverse direction, eventually I'll reach a point where the junction will break down and I'll start conducting current. And this sometimes is referred to as the Zener region. And sometimes the diode will be designed for a particular breakdown voltage. And now remember that as the depletion region, as the width of the depletion region changes, the capacitance changes. So I can also plot capacitance. Let's also plot along with the current. Let's plot capacitance. Now, if I have zero bias on the junction, I may have a capacitance here. As I increase the reverse voltage on the junction, the depletion region gets wider. So in the equation for the capacitance, epsilon times area divided by D, as I move down this curve here, the capacitance is decreasing because this D term, the depletion width, is increasing. So I get a nonlinear capacitance curve that looks something like this. So let's erase this. Let's presume that we have a silicon wafer. And I'm going to draw the surface of the wafer. Let's say the wafer has a certain thickness. This is the bottom of the wafer down here. This is a wafer. Let's say that this wafer is a p-type material. Now let's presume that in this p-type material, I want to cause an impurity. I want to dope this p region and change it to an n region. So I could put impurities into this region. And I could put in, for example, phosphorus impurities that would make this region an n-type material. When I do that, this n-type material has to have a higher concentration of impurities than the p region. Otherwise, it couldn't invert the p region and turn it into an n region. So if I know that the n region is higher concentration than the p region, what does that tell me about the depletion region? Well, remember that the depletion region extends mostly into the lightly doped material. So my depletion region, I'll draw here, will extend mostly into the p region. Now it'll extend a little bit into the n region, but far less. I'll draw part of it here, depleting a little bit into the n region. So this region here is the depletion region between this p-n junction. Now let's presume that I want to take some p material and I want to put this p material inside of this newly created n region. So this is p material, and this p material must be a higher concentration of dopants than this n material. So what does that tell us about the depletion region? Okay, let's draw a depletion region. That says that the depletion region will extend more into the n region and less into the p region. Now I can just look at this wafer, this silicon structure, and I know that this p region is lightly doped, and this n region that I added has to have a higher concentration of dopants, and this p region that I finally add in must be the highest concentration of all. So I can look at this and I can know that this depletion region between this n and p region is wider. And it's wider because the concentrations are lower. And I can know that this depletion region between the p and n material here, this is a thinner region. And it's thinner because the concentrations are higher. So I could just look at this structure and I know that the capacitance per unit area for this depletion region is small. And the capacitance per unit area of this depletion region is higher. So for the same amount of area, I get more capacitance in this upper junction and less capacitance in the lower junction. And also, I can infer something about breakdown voltage. This depletion region here is wider, So it will have a higher breakdown voltage. In this top region, this junction, this depletion region is narrower, and it will have a lower breakdown voltage. Now that we know a little bit about p-n junctions and depletion regions, let's analyze what happens in an NMOS transistor. Let's presume that, again, I have a silicon wafer, and this is the surface of the wafer, and the wafer has a certain thickness. And this is the bottom of the wafer. Now at the top of the wafer, I'm going to diffuse, I'm going to add a dopant of N material. Over here I'm going to add another N material. And I know that between this P material and this N material, I'm going to have a depletion region. It'll look something like this. And this N region over here will have a similar depletion region. Now, if I grow a glass region, let's say I grow a layer of glass on top of this structure, and I add over here a conducting electrode. And let's presume that this N region is at 0 volts, and this other N region is at 0 volts. And I increase the voltage on this electrode. I'll put a battery here to this 0 volts. And as I increase this voltage, I get an electric field in this glass region, in this insulating region, that's a little reminiscent of the electric field that is in the p-n junction. Now, as I increase this battery voltage V, this electric field becomes stronger and stronger. And what happens as that electric field becomes stronger, it pushes away holes that are in this P material. So if I have holes here, they get pushed away by this electric field. And I develop a depletion region underneath this gate electrode. And if I increase this voltage further, an interesting thing takes place. The region under this gate, under this electrode, actually inverts and goes from a depletion region to an N-type region. So this will invert, and the stronger the field, the more this inversion, and the more I drive down this depletion region. So the depletion region will move down here. So we see that this depletion region is also related to how this MOSFET transistor behaves. So when this junction, or when this region inverts and becomes an N-type region, I now have conduction. I have a conduction path from this region to this region over here through the region underneath the gate electrode. So again, this is a NMOS transistor. And we'll talk more about this in future videos, but I just wanted to give you an overview of how important this depletion region is, and that it's important for a diode, it'll be important for a bipolar transistor, and it's important for MOSFETs such as NMOS transistors and PMOS transistors.